And then this, from this one, we know charge is equal to what? Your current times your time. Okay, so it means that M is proportional to current times time. So if you know the current flowing, and then we know, if we know the current flowing, and then we know the time it is taking, we can tell. So that here, from here, we can see that M is equal to what? KIT. Okay, so this is what you call Faraday's first law. Faraday's first law of electrolysis. Okay, so electrolysis is using electrons to separate or precipitate other substances. Okay, so electrons will flow and then cause copper 2+ to form copper. Okay, so this deposit will depend on how much electrons are coming, and that the electrons is the same as charge. Electron is the same as charge. Okay, charge is given by this is the formula for charge, because current is equal to rate of change of charge over time, which means charge is equal to what? Current times time. If you are looking at the expansions, okay, so this and that. Okay, so we know also that the equivalence, you must know the equivalence. So that is the Faraday's first law. We will look at this one. Right. Now the second law, this is the first law of Faraday. The second law of Faraday, based on electrolysis, is that if this is copper 2+, the amount of electrons needed to neutralize this, to form copper from it, will be equivalent to the charge is going to be 2 electrons, 2 moles of electrons. So if it is copper 1+, we need 1 mole of electrons. If it is copper 2+, we need 2 moles of electrons. Okay, that's the second Faraday law. That the amount of charge needed is proportional to the valence of the ion involved in the process. Okay, right. So let's also put this one there. That 1 mole of electrons is proportional to what? 95000 coulombs. Okay, that's the charge. 1 mole of electron has this charge. Okay, so if you are given the charge, you can estimate how much mole. Once you know the number of moles, if you know, let's say PE 2+ plus 2E is going to what? PB. Okay, so if you know the charge that has actually flowed through the circuit for a long time, what you can do is if you know the charge, you can estimate how much the number of moles of electrons there. So if, let's say, you got 5 moles, then you can tell how much of this will be deposited. Okay, 2 moles will deposit this, so 5 moles will give you how many? That's about 10 of that. 10 moles of PB, and then from there you can estimate the mass. You know, number of moles is equal to what? Mass over molar mass, and then you can do that to do your calculation, right? So remember, copper hydroxide and copper sulfate is green. Okay, copper hydroxide, copper 2 hydroxide, and copper sulfate is green. Okay. This is copper sulfate, copper hydroxide. Okay, this is green. Okay, so if you are doing a reaction and you see it, you can detect it. Okay, sodium, potassium, they react very well with air faster. Okay, now the transition element, it may be slow. Okay, as we go down, as the charge is increasing, the reaction becomes slower. For instance, zinc, after reacting with acid, okay, or even with air, the surface that is formed, the zinc oxide that is formed, may form as a form of a protective layer and then slow down further reaction, so on. Right, so let's look at this. So when it comes to electrolysis, okay, so you are using electrons to separate. Okay, so let's say you have L3+, you let electrons flow to it, and then that will convert it to aluminium. Okay, from a solution. Okay, so you are using electrons to separate it from the solution. Okay, this is electrolysis. Usually when it happens this way, in electrolysis, where the reduction, this at this place, this is adding onto it. This is the reduction reaction. Where the reduction is going on is what we would refer to as the cathode. That is under electrolysis. Okay, so where the electrons are being added is the cathode, and then where the electrons are being released, okay, will become the anode. Okay, will become the anode. Okay, so note that it is different from the cells that we talk. So here we are using electricity to separate, not as a cell or as a battery. In batteries, cathode, they are throwing the electrons. Okay, but when you are using this to separate, at the point where electrons are adding to the cation of the metal to form the metal, where it is the reduction is going, where the electrons are being added, becomes a cathode. Right. So let's look at some reactions. Okay, so here we have a double bond. If you have finely divided nickel, then all these ones can act like more or less like a catalyst. They can provide some electron, what do you call it, like electrons in the form of free radicals or electrons to allow this reaction to break down. So this will break down so that you have a free radical here. Okay, and then if this can attract, take hydrogen atoms in the system to become alkene. So this an alkene becoming alkene. Okay, so you use the nickel as catalyst about 150 degrees, you get a good yield. Now this is the alkyne, the alkyne to alkene. If you want to reduce the double bonds, so here reducing the single double bond, we use the nickel. Reducing triple bond, you can use copper chloride. So here we have copper there, and then we have hydrochloric acid. So like you have double dose of the halide or halogen. The halogens are good free radical initiators, so they can attract, they can create free radicals in the system, which can come together as an added product to form this. So you have the two added, and then you have alkene formed. Okay, so chloro, and then the hydrogen chloride or the chloride ion can add to one of the free radicals to form chloro what? Put 1 in 3 in put 1 3 diene. Okay, right. So that is what 2 chloro 2 chloro what? 1 3 buta diene. Okay, like we've said first. Right, butadiene. Okay, all right. So that's 2 ins. Okay, that is what we have there. Okay, so let's look at this the reaction. So free radical kind of reaction, free radical kind of reaction. So nickel can help with that. The halogens can also help with reducing the whole bonds. Okay, that is the concept here. Right, now let's look at the brief summary of a benzene reaction. Okay, this is benzene, and this is cyclohexene, one double bond, and this is cyclohexane. Okay, this will give us some guidelines as to how organic compounds react. Okay, so if you look at it, this is just one double bond. So this is the pi bond, this is the sigma bond, this has 3 double bonds, this has no double bond. Now let's look at the first reaction. If they are reacting in air, with oxygen, when you are reacting with oxygen, it's the same as what you call burning. Okay, so that in terms of carbon dioxide, the carbon content, this one has higher carbon content because we have fewer hydrogen atoms here. We have relatively fewer hydrogen atoms here, but here a lot of hydrogen atoms. So the one which has higher carbon content will burn with thick smoke. So this will give us a very thick smoke. This will give us relatively thick smoke, and this will give us luminous smoke that you can see through. Okay, because of the low carbon content. that is with reacting with oxygen. Now, if you look at permanganate or potassium permanganate reaction, potassium permanganate has high oxygen in it, so its ability is to give oxygen. That means to oxidize you or to take electrons from you. So either it's giving you oxygen or it's taking electrons from you. Now this has more electrons, okay? So it means it will be able to, in the presence of, it will react with benzene. And potassium permanganate, it's brownish red color. Okay, when it reacts, it will change. Okay, so it is more or less like a self-indicator. So it will be decolorized in the presence of in reaction with benzene. Okay, and that is what you see. Right. But if you compare the reaction between cyclohexane and benzene, which one will react more? Now remember this one, the electrons are not stagnant, they are moving. So they are more or less stable as compared to this one, which is fixed. So this will react more. So this will readily react in cold. But this, you may have to heat it. You may have to add heat before you can react with the potassium permanganate. Okay, so note, this one is not going to work. Okay, right. So let me clean that up. Okay. So we move on to the next one. So no reaction for cyclohexane. Now let's come to the halogenation. Halogenation that is using bromine and then the tetrachloromethane. This tetrachloromethane is going to provide a lot of free radicals. Okay, so we're going to have free radicals. Because we are going to have free radicals, we're going to have what? A lot of reactions. Okay, it means if you have a dense electron somewhere, the free radicals can easily attack it, and then reactions will go on. So the free radical kind of reaction is going to be dominant here. So here it has something that it can attach, so to react. It has something that it can attach, so that is it. But we can look at it in the other perspective. Okay, right. Let's look at the next one. So the free radical is going to react with this. It will react with this, but like we said, this is very stable. So the reaction will be delayed somehow. It's not be easy to get the reaction going. So this will decolorize it. This is more or less, bromine also has talent for it to be decolorized, okay? But this will be slow unless you add catalyst to it before you get the reaction. But this will not react at all. Now, if you come to the sulfuric acid refluxing, that is exposing it over 24 hours, what will be the reaction? So sulfate, we have the sulfate reaction here that is going to add on some sort of reaction. Of course, this is going to give you a negative sulfate charge ion, okay, and this is what we have positive plus, okay. So how is this going to this one refluxing, exposing it to it? How is it going to contribute to the reaction? Let's see. So here, when it comes to the hydrogen we come to the sulfuric acid. If you reflux over a long period, this is going to react, okay, to form your cyclohexane sulfonate, okay, or sulfuric acid, okay. This is also going to react, but this will be slower. But if you add the acid HBr or HCl, this will not react. This will not react to this, but this will react with that one, okay. Because here the electron density is stagnant, is there, it can attack, but this is distributed, so you don't know exactly where it is at the moment. So the density is not as it is here. So this will react, H2SO4 will react, all the three will react. But here only this one will react, these two will not react. This is not going to react at all. Right. Now let's look at the next one. The same thing with this one. Right, now let's go on. Okay, so we finish with the acid part. Now we come to the concentrated HNO3 and then sulfuric acid 1-to-1 reflux. Okay, so here the nitrogen with oxygen. Remember, okay, this is making it they are all pulling, so partial positive sign will be on this, while this will be negative. Okay, so this partial positive sign is there. Remember, the sulfuric acid is also providing a negative distance. So there's a cation here, which can add on to this benzene ring and sort of stabilize instead of allowing the resonance to go on, it will localize the double bond. Once it localizes, then it means we have higher electrons stable for reaction, and therefore the with the presence of sulfuric acid as a nucleophile or as a nucleophile with electrons, it can aid in adding the nitro group to benzene, so that you have nitrobenzene being formed. Okay, right. So this will add, but in the case of this one, this will not react. Okay, this is not going to react with this one. Okay, the nitro will not, of course, it's not going to look at, it's not going to aid with, there's no resonance here for it to stabilize or distribute, and that reaction doesn't go on. Right, so if you look at the next one, that is a Freda-Kraft reaction. The Freda-Kraft reaction uses the chloromethane and then aluminium chloride. So the aluminium chloride is given a positive charge. Okay, that positive charge can localize, sort of bind to the ring and localize the double bonds. Okay, once it stabilizes it that way, any free radical can then attract or can participate in either attracting an electron, so that it adds onto. So you can add the chlorine on the bromine or chlorine onto the ring, right? In that case, what will happen is so what will happen is, let's say we have that is Freda-Kraft reaction. We have our CH3 as a radical coming, and then we have Al plus 3 plus here. So when it is here, it's more or less helping to localize the electrons, okay? But it will not react because there is an ion, okay? It's just localized. By localizing it, it provides an opportunity for this one, Cl. Okay, this can break to become Cl minus and this plus, okay? So this C plus here, methane can add onto the benzene ring. So you can have methylation of the benzene ring, okay? And that is common with that kind of reaction. You can have 1,2 diameter 1,2 diameter benzene being formed, or 1,4 diameter benzene being formed, okay? So that is the reaction for this one. Right, so that is the Freda-Kraft reaction. But that will not occur for this one. You can just actually tell, because this one adding on to is not really going to localize that one, okay? So you will have it an easy reaction going. So no reaction, because this is positive, and that one is there, it's not going to add on to easily, okay? But because this one localizes and then it increases the presence of double bonds become high, then this can easily add. But this one will have only one double bond, so the activation energy may not be enough for the reaction to go on. Of course, cyclohexane will not react at all. Then you come to hydrogenation, adding hydrogen, okay? So adding hydrogen, if you have nickel, it also provides something like a free mechanism, it's a catalyst, okay? So that can add on to this one. And of course, this is this is not localized, but that reaction can go on to some extent, right? Okay. But of course, you need higher temperature for this hydrogenation to go on in the case of benzene. Now let's look at the next one, halogenation, using aluminium chloride as a cation center. So once it localizes, these free radicals can add on to. So the reaction will go on with benzene, okay? But in the case of this one, if this is not going to, it's already localized, so it's not going to add on. Adding on this one, chloride and all that, will not be as smooth as, of course, if in the presence of this, it will not allow the reaction to go on smoothly. So no reaction will occur with this halogenation using the aluminium plus here. Okay, once it localizes, the B plus cannot go on, for the density of double bond will not be that high for the addition reactions to go on, right? Now let's look at the last part. This is the halogenation in the presence of UV light. UV light is going to generate a lot of high free radicals. So virtually all of them will react, okay? This will react to full, this will react to full. So you get all the reaction getting to its end, okay? And then this will also have some addition of bromine or chlorine atom being added. So in this process, benzene hexachloride, which will be formed. So chlorine, 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 benzene hexachloride, called lindane. It's an insecticide, okay? Can be formed. Okay. Right. It's also called gamazine. Okay, right. So let's look at the next one. So just briefly, let me just talk about this: the halogenation reaction, then the Friedel-Crafts reaction. Friedel-Crafts reaction will add the aluminum component. The aluminum component is charged 3 plus. Okay, so it will localize the double bonds. Okay, for the next reaction to occur. Right, but let's see what happens. In the case of just one double bond, if it's already localized, so if this one adds, it's still the same thing. That means you need a stronger free radical. So unless something that can provide more free radicals, like maybe tetrachloro methane. But if it is just chloromethane like this, it will not react. It will not react with the cyclohexane. But in the case of benzene, this one localizes it. You have more double bonds, and even just chloromethane will also add on. So you have methylation of this one. Okay, right, but not the chlorine that is going to be added, because this is providing, it's just localizing it. So you have more electrons dense. You can't add another electron dense to it. Right. So that brings us to the end of the various reactions. So you can look at it about how many reactions: 1, 2, 3, 4, 5, 6, 7, 8 in perspectives. Okay, most of the reactions are not going to occur for cyclohexane apart from burning in oxygen, and then in the presence of UV light, where we have a high lot of free radicals being generated, which will allow cyclohexane to react. Other than that, most of the other reactions it will not. Okay, good. Now let's look at intermolecular forces. Okay, there is one molecule, there is another molecule. The only force that can exist between these two will be weak van der Waals forces. We have talked about this already. So it will be weak because you just need this one to have instantaneous negative and instantaneous positive. Okay, before they can attract. So induced dipole, that is very weak. So the bond between this one is very weak. Unless it is a very long chain, then you have it being stronger. If it's small, it's very weak. Now here you have oxygen here, which is polar. So if you have another and has double bond, if you have another H in a system, they can form hydrogen bond, which is stronger, and that system will be stronger. So this kind of bond will tell how the boiling point will be. So it is weak, so it will easily, when it is heated, it will just evaporate easily. Okay, van der Waals. If it is hydrogen bond, where we have charge, this is more charge. So this one is induced dipole, induced dipole. So this is weak. If it's hydrogen bond, then the boiling point will go up a little. It will be. If it is more charge, like charged particles, then it will be greater. Okay. So but usually you have van der Waals forces and then the hydrogen bond. Okay. This. Okay. So depending on which one, the boiling point. If it is hydrogen bond, boiling point will be higher. If it is van der Waals, it will be lower. It means if it is lower, it means it easily evaporates. If it is higher, it means it doesn't easily evaporate. Okay, right. Now let's look at these reactions. Okay. Now if you look at this one, this is an alcohol. So alcohol, it has a C. So it has this one. Okay, so this is potassium permanganate. It is an oxidizing agent. Oxidizing means it will help you to it will add, it is an oxidizing agent, so it will give you oxygen. Either it will give you oxygen, or it will take electrons from you, take electrons from you, or it will take hydrogen from you. Okay, so look at it in that principle. This is an oxidizing agent. oxidizing agent, so it will help the other product or substance to be oxidized. Okay, so either it will add oxygen to you so that you become oxidized, or it will take electron from you so that you become oxidized. If you add electron, you reduce. If you take it, you oxidize the thing. And if you take hydrogen from the compound, or the compound, you have also oxidized it. But if you add hydrogen to it, let's say hydrogen radical to it, or hydrogen component to it, then you have reduced it. So taking away hydrogen is oxidation, taking away electron is oxidation, and then adding oxygen is oxidation. So let's see what will happen here. So this is a good source of oxygen, it's an oxidizing agent. So to add oxygen to this component, but it also has a redox reaction. That means it can provide free electrons movement. Okay, so this, or it can handle free radical or free electron movement. So it means it can attract electrons, it can take one of each away, okay, and then add oxygen. Okay, so in that case, you can take this one away. If you take this one away, because this is easier to take than this, okay, because this is negative, this is positive, this bond is weak, okay, there's a shift in the bonding, so this can easily take away this hydrogen. When it takes it, this is going to the free radical here, and then that here, okay, there's one here. This can go together to form C double bond. So we have C here, we have our H here, and then we have our C, and this becomes what? An aldehyde. Okay, so an aldehyde formed. The process can go on, okay, if you keep on doing it, okay, adding. Then it can, the next thing is, it still has hydrogen here on top here. It can take this hydrogen off. If it takes it off, the free radical is here. Remember, it has the potential of adding oxygen, so you can add oxygen, and then you can get alkanoic acid being formed as this one. So in concentrated concentrated sulfuric acid with MnO4, you can form this one. Okay. So in the case of alkaline, let's see what happens here. In the case of alkaline solution, the same oxidizing agent. Okay. So here, the one that can be easily abstracted. Of course, here the hydrogen here can be taken off. When it's taken, oxygen can be added, so it can go through the process like we said here. And add, but because here we need to add we need to be adding more oxygen. It's in an alkaline solution, so OH is there. Okay, that can add up to give us this phenol what the benzoic acid. Okay, with what do you call it? The compound attached to it. Right. So that is the phenol methanoic acid. Okay, good. So if we come here, remember this week is carbon relatively weak. Okay, so if we have hydrochloric acid here, the H plus, this is these two are not the same, so there's polarization. Okay, so let's say this becomes a little negative, this becomes a little positive. The H plus can add onto the lone pair here, like hydrogen bond, and then cause this one to be disrupted. So you can break this one down, and then this will be, you have a free radical here. Because it's in dilute solution, water can add on. So water adding on, if the process goes on, you can take off all these the two bonds here, and then form the acid form. You can form the alkanoic acid from that direction. Okay, so that is dilute HCl. Okay, now let's look at this. This one is an ester. Okay, it's a little different from the alkanoic acid anhydride. This is an alkanoic acid anhydride. Remember, this one is like two acids coming together. So this one is like an alcohol or an acid coming together, but there's no OH here. Right. So here, if you heat it with H plus, where will the H plus go? This can cause this one to be negative a little, and here will be positive, or it can come this way. So if it is like this, your chloride, of course, can push, okay, or anything, water, if it's water there, the OH minus the little, it can push it way here, okay. If it is pushing it way here, then there's possibility that this can be displaced. This bond can be displaced, okay. If it is pushing it weak here, then this bond can displace. If this bond is displaced, this is going to form alcohol. That's going to have you, and this is going to form the annoying acid. Okay. Right. Your H plus will not be strong enough to go in and then form the bond, because you need a greater density to do that interaction. Because if it does, the stabilization of this bond, double bond, will not go on board. Okay, so you need a stronger distance to do that. But it's the dilute one, so more water in there, so more water can compete and out-compete any other reactant. Okay, so the nucleophile as the water becoming the nucleophile going into this one, which is the electrophile, to push, and then because this bond this is pulling electrons, so it will make the carbon as an electron positive. This carbon positive will try to pull electrons here. Meanwhile, this is also trying to pull electrons away, so this bond will be weak. Okay, and that is why it will break into this. Now, when it comes to the sodium, the same thing here. Once this bond is weak, remember here, OH minus can attack. Okay, OH minus can attack, and then displace and form this. But of course, when it forms this Na is there. Sodium is there. Sodium can replace the hydrogen here, and then form this. Right. Okay, so that is pulling this through. This is the reaction you can get. Now let's look at this reaction. So here this is an acid. Okay, it's reacting with magnesium. Okay, so acid reacting with metal. Okay, of course this will replace the hydrogen here, and then form hydrogen gas. And then because it's Mg2 plus, it will need 2 of this. That's why 2. So we have magnesium alkanoic acid. Right. The next one, let's look at the next one. Here, acid reacting with ammonia, which is base. Okay, so this, of course, is an acid-base reaction. So this will be added to make the ammonium carbon, the ammonium cation, which will add to the acid. Okay, so this ammonium alkanoid. And then upon heating, if you heat very well, okay, remember this is pulling electrons. So you can be pulling the electrons to the center. This will be coming, and this will be going. Okay, that can weaken this bond. One, this bond two. If this becomes positive, it will also attract. This bond can also be weakened. Okay, so depending on what is there, this will break or this will break. Okay, right. So this one is nitrogen here. It has lone pair on it. Okay, it may leave and then dislodge this one, giving an OH, pushing this one, and then adding the amine group. Adding the amine group to it. Okay, so that you have going to have this H and H here, right? Adding the amine group to it, and then that is becoming